Matrix inverses. The identity matrix is a square matrix that has ones down the main diagonal and zeros elsewhere. Here are some examples of the identity matrix. We have 1 by 1, which is just scalar, 2 by 2, 3 by 3, and 4 by 4 identity matrices. Notice that only the main diagonal has ones and we have 0 everywhere else. In general, we use the notation I subscript n for an n by n identity matrix. Another useful notation is Kronos Delta. The Kronos Delta is a function that takes two inputs, here I and j, and if I is not equal j, the function takes 0, and if I equals j, the function value is 1. In linear algebra, the notation we can use for the identity matrix is that the ijth entry of the matrix equals delta. We can easily see that if I equals j, that entry of the identity matrix is 1, otherwise it takes 0. If A is an m by n matrix and we have an n by n identity matrix, then A times the identity matrix equals A. Similarly, if we have an m by m identity matrix, I times A equals A. Hence, the name identity comes from the fact that if we multiply it by any matrix, the result will be the same matrix, so long as the dimensions are correct. Now we can define the inverse of a matrix. If A is an n by n matrix and we have its inverse, then A times A inverse or A inverse times A must be the identity matrix. In this case, we say A is invertible. For a 2 by 2 matrix, if the determinant is non-zero, we have a handy formula that we can compute the inverse easily. And the formula says 1 over the determinant times a 2 by 2 matrix, where you see we swap A and D and negate B and C. For example, here we have a 2 by 2 matrix. If we use the formula, we learn that its inverse is the matrix you see. We can verify this in Julia. If we define A and B, we see that A times B and B times A both are the identity matrix. If a matrix has an inverse, its inverse is unique. That means that there's only one of them. So therefore, if A times B equals B times A equals the identity, then B must be the inverse of A. To see this why, suppose A times B equals the identity and A times C also equals the identity, meaning C and B both are the inverse matrices for A. Now if we subtract these two equations, we get A times B minus A times C equals 0. We can factor A, and we get B minus C equals 0. Now, A cannot be 0 because we are talking about invertible matrices. Therefore, B must be equal to C. So we learned that the inverse is unique. Suppose A is n by n. Because the determinant of a product is the product of the determinant, we have 1 equals the determinant of the identity equals the determinant of A times A inverse equals the determinant of A times the determinant of A inverse. Now, a useful consequence of that is this relationship. We can find the determinant of the inverse of a matrix if we know its determinant. If the determinant is non-zero, then A has an inverse. Or we can say A inverse exists. Putting everything together, we can say that an n by n matrix is invertible if and only if its determinant is non-zero. Another useful fact is that A times B, if we take its inverse, we get B inverse times A inverse. Notice that the order is swapped. The reason is that if we multiply A by B, and the claim is that B inverse times A inverse is the inverse of the product. Because matrix multiplication is associative, we can write A times B times its inverse times A inverse. This will give us the identity. A times the identity matrix will give us A, and A times its inverse is the identity. Therefore, we prove that A times B, its inverse is B inverse times A inverse. If A is invertible and we have its factorization as L times U, A inverse therefore will give us U inverse times L inverse. The matrix inverse is useful for deriving closed form solution to linear systems of equations. If we have AX equals B, then the solution is A inverse times B. However, we rarely compute A inverse in practice and multiply it by the right hand side. It's much preferred to compute the factorization and use forward and backward substitution. And the reason is numerical instability that might be caused by inverting A explicitly. Another reason is that if there is any special structure in A, for example, if A is a sparse matrix, meaning it has many zero terms, A inverse in general will not preserve that, and it will be a dense matrix. So if we could get any efficiency by using the sparse structure of A, we won't be able to do that by explicitly inverting it. Next time, we will talk about matrix transpose and symmetric matrices.